Hi, pre-calc people. Welcome to your first introduction to calculus, which is going to be limits. Limits is a connecting concept between differential and integral calculus, and we'll be looking at an intro to both of those branches. In all, we will be looking at each concept graphically, numerically, and especially algebraically. Numerically tends to mean you're looking at the table in a calculator. So let's start off with limits. So we have this kind of ugly definition here of a limit. I'm going to read it out and then kind of talk about what it means. The limit of f of x, which remember that's the y value, as x approaches c. So as your x values, as you're coming along, as x is approaching a particular c value, notice that your output, your y value, your f of x, is approaching a particular limit, whether that value is there or not. And what we're going to look at is how we can find intervals around our C value to keep our output around our limit within a certain amount. The way I like to think of this, just to make this really short, is if you're a manufacturer and you're manufacturing pipes, and your pipes have to be able to fit into another pipe, and you happen to know that there is an acceptable error in the output where the pipes will still fit, obviously on a micro unit level. Okay, so you know that with an acceptable amount of error, next year you'll call this epsilon, around the limit, you can work backwards to calibrate your machine so that the input will make sure that it keeps the output in that limit. This is what we're going to do algebraically right now, okay? I know we're starting off with actually a harder concept than the rest of calculus. I think limits are harder than the rest of it, but that's okay. We're going to do this in a very nice way. So I have a graph down here. The graph is a little bit skewed because this hole should look like it's right above the 3, so we're going to pretend like it is. I'm not sure what happened. I just copied it from the book. So if we look at this graph, we want to see, well, what is f of 3? So it looks like at f of 3, there's no value there. So f of 3 does not exist because there's a hole there. It's a removable discontinuity. Now, what I have below that graph is an equation, and we're going to simplify this equation so that we can find what was that value of f of 3 before it got removed. So we want to factor the numerator, and you might be like, how do I factor a cubic? We're going to do our synthetic into it to see what that would be. So remember, you put the 3 in the box, then we have a 1, the coefficients on your numerator. Here's an 8, -6. You drop the 1, multiply, add, multiply, add, and multiply. So notice it is factorable. This factors into x minus 3 times x squared minus 2x plus 2 divided by x minus 3. You did these when you were doing your rational functions and having to graph them. So we can remove this factor, which that's what results in a removable discontinuity. But now I can find that f of 3, when I plug it into this equation, 3 squared minus 2 times 3 plus 2, you get back 5. So what's going on here is, as I'm approaching from both sides, my graph is approaching, the limit as x is approaching 3, so the x values are approaching 3, my y values are approaching 5. That would be my limit. All right, and that seems to make sense with what we see in the graph. Now what we're going to do is talk about that boundary of error that is allowed. So we want to find the biggest possible interval around c equals 3, but not equal to c because that would make my denominator 0. But we want to keep our limit, which we now know is 5, we want to keep it within 0.1. So that means, I'm going to exaggerate this just because it's hard to draw 0.1. So that means I'm looking at 5.1 and 4.9 if I carry these over to my graph and follow them down. So I know I'm allowed 0.1 error around that limit of 5, and I want to find what are the corresponding inputs that keeps me in that interval. So the way we do this is we set our two boundaries, so 5.1, and we set that equal to our simplified x squared minus 2x plus 2. This is where your quad program on your calculators is going to come in extremely handy. So I set this equal to 0. So that's x squared minus 2x minus 2.9. Oops, sorry, I did the wrong one first. 5.1, that's going to be minus 3.1. And then by the quad program, so again, you're going to want, unless you're really fond of doing the quadratic formula, and that's fine, whatever floats your boat, you'll find that you get x equals 2.975, or, because it's going to give you two answers, negative 0.975. And since we're trying to find an interval around 3, we want to choose the number that's going to be close to 3. So for 5.1, 2.975 will be on one side. And then we do the same thing for 4.9. We set it equal to the equation, which we then set equal to 0. Now I've got my minus 2.9. You use your quad program, and it's going to give you x equals 3.025 or negative 1.025. Again, we want the interval that's around 3. Sorry. And so we're going to choose this one. So corresponding to 4.9, oh, I wrote those on. I'm so silly. Silly me. So corresponding to 4.9, I got an interval here of 3.025 and 2.975. And that would be the interval that keeps us within, so if I keep my x values within, or I should say my c values, within these two numbers, it will keep my limit of 5, or the limit, it'll keep anything within 0.1 of my limit. Now, how do we know that is really true? We can choose any value in this interval that we just came up with and show the output really is 0.1. So what you're going to do is just choose any value you want. I'm going to choose x equals 2.99. So we find what is f of 2.99. You plug it in to your calculator, and I get 4.9601, which is less than 0.1 of 5, because it's above the 4.9, which is what we wanted. All right, so that would be doing algebraically. So you're going to simplify your rational expression so that you're not dividing by 0, and then you're going to set that equal to whatever the parameters are. In this case, it was 0.1 above and below our limit, and then find what the corresponding input would be to give you that output. How would you use your do this numerically, I would use my table feature. So under y1, I would enter x squared minus 2x plus 1. Was it what? It was 2. 2x plus 2. And then I would, for my table set, I would look at I would do increments of 0.01, and I would then just look down the table of values. I don't really do them numerically because it's just looking at data, and we can do it algebraically, and we can also do it graphically, which is what we're going to continue on with. So normally I would say, okay, you guys try it with a new function, but obviously this is a lesson, so I'm going to go through it slowly, but if you want to try this first, turn off the video. Might not be a bad idea. So we have a function here. Our function is 2 to the x, a nice exponential function. And 2 to the 1 is going to give me a limit of 2. So here is the c value that my x's are going to be approaching. And we want to find the input that keeps my output within 0.1. So again, we're looking for an interval around 2, so 2.1 and 1.9. That will keep my function within that limit. So we're looking for our input. So you're going to take that 2.1, set it equal to your function, and we want to solve for x. And the reason why I chose this one, of course, is because it forces you to do a log problem. So you take the log of both sides, and that allows you to bring the x down. And so then we divide by log 2, and you get that x is going to be 1.070 for one side of it. So this would be 1.070. And then we do the same thing for 1.9. So this will give me log of 1.9 equals x times log 2. And then we're going to divide by log 2 so that we get x equals 0.926. And that would, so here is the interval that will keep sort of the input that keeps my output within 0.1 of my limit. And if we want to verify it, you can choose any value you want within this. So again, I'm going to choose 0.99. So what is f of 0.99? So 2 to the 0.99 is approximately 1.986, and that is within 0.1 of your 2. So it is within our output. Okay, so that is doing a limit algebraically. Next year you're going to have epsilons and deltas involved in this as well, but it'll be okay. Here's my favorite part, the graphing. Finding limits graphically is kind of fun. You're going to be using your fingers, your pointer fingers. Unfortunately, I can't demonstrate this. To me, this is very physical, so I'm going to try and draw what I'm doing. If I have a graph, now you've seen limit notation before. This is not something new. We've done limits before. If you have a graph and f of x is approaching your limit as x is approaching the input from the right. So from the right means from the positive side. So you're approaching from the right. So this is how it would look. We represent that down here with a little plus on whatever. So I'm approaching C. Where can I draw this that you can see it? Down here on the graph right below, I'm putting in an arrow around x equals 1. That would be approaching from the right. And again, we use a little plus because you're approaching from the positive side. If I'm approaching from the left, we put a little negative because you're approaching from the negative side. So this is approaching from the left. So it's like I'm looking at what I'm going to get when I approach from the left. If we want to approach from both sides at the same time, which is just your limit, it's not a one-sided limit, then we have no plus or minus, and this is the notation. So this is doing both sides at the same time. These two up here are called one-sided limits. So you're only approaching from the left or you're approaching from the right, and we're going to talk about how you analyze this. So let me get rid of this, and let's do some of these. So the limit as x approaches 3, no plus, no minus. What that means is I'm looking at, so here is x equals 3. I'm approaching from this side and from this side. The answer to your limit is always a y value. What is the y value that you are approaching from both sides? And we can see as we carried over that that y value is 5. Now we're going to approach 1. So here is how this works. We're now going to approach 1. Notice I think of this as, okay, from the left, I'm walking to a friend's house. From the right, you are walking to the same friend's house. It doesn't matter that our friend is not home. They've gone next door to get some, I don't know, some butter, whatever, okay? The fact is we're still both approaching the same value, even if that value has a hole there, even if the value is not defined right there. We're both approaching that same point, and so that limit is 2. The actual value of f of 1, like where is our friend? Our friend is down here at 1. They are next door. Okay, so there is a limit. There is a point that we're both approaching the same house. The house, even if there's no one home, we're still approaching there. Okay? Now, let's look at what happens when you do one-handed limits. One-handed, one-sided, sorry. Okay. Limit as x approaches 2. I'm going to kind of erase things as we go so this doesn't get too crazy looking. So here's 2. If I'm approaching 2 from the left, because notice there's a little negative here, the y value that I'm approaching, again, doesn't matter that no one's home, I'm still approaching a value of 3. Okay? It's a limit. It's not saying what is the actual address, it's what are you going to, because you don't know until you get there whether anyone's home or not. You're still approaching that point. Now, as I am approaching 2 from the right, that's up here. So as I'm approaching 2 from the right, the y value is 4. So if the blue is me and the green is you, as we're both approaching an x value of 2, notice we're actually approaching 2 totally different houses. 3 and 4 are not the same place. It's not the same value. So when you take away the plus and the minus, this limit does not exist because those 2 values up here are not the same value. In order for the limit to exist, you have to have the limit of the plus equal the limit from the right equal the limit from the left to have an overall limit. So again, I want to go back over this because it's important. The limit approaching 1, even though you weren't home, we were still approaching the same house. Okay, just there was a hole. We were still approaching the same house. But when we're approaching at 2, we're approaching 2 totally different addresses. And so there is no overall limit there because it's been split up. All right, let's kind of continue this. The limit as x approaches 4, here's 4. Notice it's a nice smooth curve. There's nothing, no problems here. So as I'm approaching 4 from both sides, we're both approaching the same y value, the limit is 3. And then lastly is the limit as x is approaching 5. Now notice from both sides, the behavior of your graph is the same. However, so there's like an asymptote here at 5. Since there is no value, the easiest answer is to say the limit does not exist because the graph is growing without bound. It's not ever gonna stop. It keeps getting closer and closer, but it never actually gets there. The graph grows without bound. So the easiest thing to do is say it does not exist. Now, sometimes, let's say you're taking a multiple choice test. It may not have an answer of does not exist. It might give you the answer of positive infinity, which says that is the behavior of the graph. The graph is approaching a positive infinity from both sides. You will never have a multiple choice where you have to only choose one answer that would have both does not exist and positive infinity, because they're both correct. One describes the behavior of the graph. One is the fact, well, infinity is not a limit. It grows, it's going on forever to infinity. So that's the same thing as saying does not exist. All right, you're gonna get a lot of practice with this, so hopefully it'll eventually come around. Okay, let's keep going. Now you're gonna have to come up with your own graphs and figure out these limits. And this first is gonna be a parent graph that we're gonna work a lot with. F of x equals the absolute value of x over x. So when you look at that, it's basically 1 unless the denominator happens to be negative, in which case it would be a -1. And if you're not sure, you can we can plug in some values. Let's start with like -2, -1, 0, 1, 2. If I plug in a -2, I get 2 over -2, which is a -1. A -1, I'd have +1 over -1, which is a -1. At 0, nada. At 1, you're going to get 1 over 1. At 2, you'll get 2 over 2, which is 1. So your graph will look like this. At 1 and at -1, so when x is 0, nothing exists, but then it'll always be either 1 or it will be -1. So your graph kind of has this step function look to it. All right, so that is the graph. What are the one-sided and two-sided limits as x approaches 0? So the limit as x approaches 0 from the left, that's from the negative side, that limit is going to be a -1. The limit as x approaches 0 from the right, from the positive side, that limit is going to be a +1. All right, so for this one, we're looking at it as we're approaching from this side. For this one, we're looking at it as we approach from this side. Together, since they are different numbers, when these do not match up, that means the limit as x approaches 0 does not exist. So we do have one-sided limits, but when those one-sided limits do not agree, the overall limit does not exist. Okay, so let's do some algebraic limits. If it helps you, you can draw a graph and think about what the graph would look like. So here we have a rational equation, x over x plus 3, and we want to know what is the limit as x is approaching a -3. Well, if I were to plug in a -3, notice I would get -3 over 0. So we know that there's a vertical asymptote at x equals -3. What does that mean for the limit? It means that the limit does not exist. All right, because you have an asymptote. We could talk about the behavior, but you don't have to. You can just say the limit as x approaches -3 for this particular function does not exist, because you have an asymptote there. How about this next one? X minus 2 over x plus 4. Well, this one, yes, it has an asymptote at -4, but at 4, it's a nice continuous graph. If what you have is a nice continuous graph, then your limit is the result of just plugging in x equals 4. So 4 minus 2, like what is the output? If your input is 4 and there's no problem, it's a nice smooth graph, the output is going to be whatever f of 4 is. So that's 2 over 8. So my limit as x approaches 4 of that function is going to be 1/4. So anything where there's not a problem with disconnect or asymptotes, it's just a nice smooth curve, you just plug in the value. Now sometimes you might have to simplify. So this next one, I can't plug in -1 because I would get 0 over 0. This does not equal 1 and it does not equal nothing. It's actually called the indeterminate form. Later on, you're going to get some strategies for dealing with indeterminate. What we want is something that we can actually determine. So what we're going to do is we're going to factor this puppy. So on top we have x plus 1. On bottom we have a difference of squares. And so I can remove, again, there's that hole that'll be in the graph. So yes, there's going to be a discontinuity. There'll be a hole in your graph at -1, but remember, as you're approaching from both sides, it doesn't matter whether that hole is filled in. The house is still there, whether anyone's home or not, doesn't matter. You're still approaching the same point from both sides. So now that I've simplified it, I'm allowed to just plug in -1, so that's going to give me 1 over -2, and that will be my limit. So asymptotes are going to give you a limit that does not exist. A hole, if it's still from both sides, approaching that same hole from both sides, is okay. Now we have the same, so we looked at the parent graph of your absolute value of x over x. This is with a vertical dilation of -3. So how does that affect the graph? And if you're not sure, go ahead. You can always plug in points, but it's going to be multiplying what we had before by a -3. So where it was a -1 becomes a -3, and the graph is now going to go that way because you're also reflecting. That's what that negative does. At 3, the graph is going to look like that. What I always do is I plug in a number on either side of 0. If I plug in 1, I get -3 over 1. So at 1, I'm at -3. If I plug in a -1, I get -3 over a -1, and that's going to be, put me up here at 3. Okay, so now we can do the limit. As x approaches 0, color code this, from the left, from the negative side, what is my limit? It's a +3. Again, your answer is the y value. As I'm approaching from the right, from the positive side, what's my limit? It's a -3. So what is the overall limit? Does not exist because those two limits are not the same thing. All right. Okay. Now, what do you do if you're looking at the limit as it approaches infinity? This is exactly what we did to find horizontal asymptotes. Because remember, a horizontal asymptote is what's the value, what is the y value as x is going out to infinity, as it's growing without bound, both positive and negative. So here's the 3 cases to look for. If your graph is top heavy, what that means is the power of x is greater on top than it is on the bottom. So that means in this, if I were to plug in values, since x squared rules, it's the one that's growing the biggest, the fastest. This means this graph is growing without bound when you're top heavy, kind of like what's happening when you approach a vertical asymptote. And again, I should put a plus or minus here. So as x is approaching plus or minus infinity, it does not exist. Think about a parabola. A parabola is top heavy because the graph is y equals f of x, x squared, right? Your graph is growing without bound. Because again, we're talking about as x goes to infinity, the graph is just going up and up and up. There is no limit. It grows without bound. So there is no limit. If your graph is bottom heavy, that means the power of x is bigger on the bottom. Something like 1 over x squared. Well, we know in a graph like that, if I were to graph it, it looks like this. So as x is going out to infinity, and x squared is getting bigger and bigger and bigger and bigger, your numbers are getting smaller and smaller. So the limit is always going to be 0. In other words, your horizontal asymptote would be the x-axis. You would have a horizontal asymptote, it would be the x-axis. And then this is the one we did to find that when you have the same power, that gets you your horizontal. So if I made this, let's say I'm just making stuff up. 4x minus 1. Okay, so remember, we're taking a limit of this function as x is going to infinity. So we're plugging in huge values of x, like 1,000,000. This plus 2 and this minus 1 are not going to really affect 3 million over 4 million because we're plugging in a huge value for x. So what happens is it's going to be the reduced form. This is just like finding your horizontal asymptotes. When you have the same power, you just pick off the coefficients, and for this particular one, the limit would be 3/4. Here it will be the ratio of the coefficients on the powers of x, on your power of x. Okay, the highest powers of x, really. Okay, so let's do a couple examples here. And now when you guys go into calculus, they're going to have you dividing by all the powers of x, and they're going to have you do all these really long ways to do it. Basically, top heavy, bottom heavy, same power is eventually what you get to. It's the shortcut that just gets you your answer without a lot of grunt work. You're going to have a lot of grunt work you're going to have to do along the way. So here, this first example, number 7, the limit as x goes to infinity of 2x over x plus 3. So I notice that I have the same power of x on top and bottom. So when I look at the ratio of that, it's going to be 2. Because you have the same power. In other words, what was your horizontal asymptote? The horizontal asymptote would have been 2. This next one, limit as x goes to negative infinity, which doesn't really matter here, negative x over x squared minus 1. Notice that I am bottom heavy because I have a higher power on the bottom. That means as my x's get bigger, the numbers get smaller, so the limit would be 0. And then this last one, limit as x goes to infinity, x cubed over x minus 4. This one is top heavy, which means this, as I'm plugging in bigger and bigger values of x, the output is just going to get bigger and bigger. So this is going to grow without bound, which means that limit does not exist. All right, so there is your introduction to limits. Algebraically, graphically, not so much. You can do it numerically. You can look at the table of values. That's hard to do through this distance learning. But for the most part, we've covered what you'll need to know.